So note that in the transition matrix from T to S, the jth column is the coordinate vector of Wj with respect to S. Okay. In other words, this column is the coordinate vector of W1 with respect to S. This is the coordinate vector of W2 with respect to S. This is the coordinate vector of W3 with respect to S. Okay. And so if we have a vector V, say equal to 5W1 minus 3W2 minus 12W3, meaning a vector with coordinate vector with respect to t given by 5, negative 3, negative 12, then we can obtain the coordinate vector of V with respect to S by multiplying the vector, rather the coordinate vector of V with respect to t by the transition matrix from T to S. You can check that the coordinates are given by 1, negative 1, 2. In other words, as a linear combination of elements from S, V is equal to 1 times V1 plus negative 1 times V2 plus 2 times V3. And this is actually consistent with the initial representation for V as linear combination of vectors in S. Here's another example. So consider R3 and ordered bases S and T as shown. So note that S and T are not the standard bases for, not the standard basis for R3. So let's take a vector in R3 such that the coordinate vector with respect to S is 1, 2, negative 1. Then what is the coordinate vector of V with respect to T? So to find that, we have to determine the transition matrix from S to T. And to do that, we have to find scalars A1, A2, A3, B1, B2, B3, C1, C2, C3 that make this system of vector equations true. So note that in the first vector equation, we are looking for the coordinates of 1, 0, 2 with respect to t. In the second, we are looking for the coordinates of 0, 1, 3 with respect to t. And in the third, we are looking for the coordinates of 1, 1, 1 with respect to t. So each vector equation is a linear system of 3 equations in 3 variables. We can solve each system individually, but to get to the desired answer immediately, we will treat all of them at once. Note that the system of vector equations is equivalent to the following linear system. So essentially, the first vector equation in the last slide is given by this first column equals the product of this matrix by the first column here. The second column is the product of this matrix by this second column. And the third column is the product of this matrix by this third column. Also, recall that in this matrix, the first column is the coordinate vector of 1, 0, 2. The second column is the coordinate vector of 0, 1, 3. The third column is the coordinate vector of 1, 1, 1. In other words, these columns are the coordinate vectors of these vectors from S. So this is this matrix of variables is the desired transition matrix from S to T. So we solve this by applying Gauss-Jordan. The associated augmented matrix of this system is given by this 3 by 6 matrix. Okay, so this is the matrix of coefficients. This is the matrix of constants. So I will leave as an exercise to check that this is row equivalent to this matrix in reduced row echelon form. Anyway, the details are all in the module. This tells us that the transition matrix from S to T is equal to this matrix. Okay, so we are now ready to determine the coordinate matrix of V with respect to T. So this is obtained by multiplying the coordinate vector of V with respect to S by the transition matrix that we obtained. And you can check that the result is given by the 3 vector with components 30, negative 26, negative 6. And we can check that V, the vector with components with respect to S given by 1, 2, negative 1 is equal to the vector 0, 1, 7, which is equal to the vector 13 times 2, 1, 1 plus negative 26 times 1, 0, 0 plus negative 6 times 0, 2, 1. The idea in the examples earlier can be applied to any vector space with any pair of ordered bases. But when V is Rn, the process for computing the transition matrix from S to T can be briefly summarized into a 3-step process. So to determine the transition matrix from S to T, we first form the augmented matrix TS. So on the left, we put the vectors in the basis T. On the right, we place the basis vectors coming from S. And then we reduce this to RREF. So we apply elementary row operations to reduce this to RREF. The columns in T are linearly independent. So you will always arrive at the n by n identity matrix. So when the matrix is already in RREF, the matrix on the right, say P, will be the desired transition matrix from S to T.